Hey everyone, welcome back to Abstract Algebra 1. This will be lecture 16 of the course. And in this section, we're going to discuss, once again, homomorphisms, this time in the context of rings. So let's go ahead and jump into it. We'll call this section 3.4, Ring Homomorphisms. Right, and so obviously, if you've been going through the course sequentially, you will know we have discussed ring homomorphisms in the context of group theory, and now we're going to extend those results to rings. Right, so we'll start with a definition, because the definition will naturally be a little bit different. It'll be just an augmentation, really, of the previous definitions that we saw. So a ring homomorphism, okay, a ring homomorphism phi from a ring R to a ring S is a mapping from R to S okay, it's a mapping from R to S that preserves the two ring operations. Okay. Right, and so what do we mean by preserve the two ring operations? Well, for all A and B in R, addition is preserved, so phi of A plus B equals phi of A plus phi of B. And in the case of rings, we also have a multiplication operation, so phi of A times B equals phi of A times phi of B. Okay. Okay, and so this is, a very natural extension of the concept of a group homomorphism to rings, right? Namely, the addition of this, the adding in of this secondary consideration regarding the new operation. Okay, and then just like before, if phi is 1-to-1 and onto S, then it's called a ring isomorphism. So if phi is 1-to-1 and onto S, then phi is called a ring isomorphism, right? So just like with groups, same terminology applies here. Okay, so that's the definition of a ring homomorphism, and a lot of the content of this section is going to mirror the content that we had with group homomorphisms. So some of it won't be there, some additional things will be there. But we're not going to go through all the minutiae of detail surrounding all of the properties and proving everything. Really what we're trying to do is just kind of naturally extend the group homomorphism concept to rings, and then provide some examples. And then we want to kind of explore some of the subtle connections between some of the other ring concepts that we've seen and homomorphisms. All right, so let's start with just a nice schematic here of what's going on. All right, so we've got two rings, R and S. Okay, and inside of R, we've got an element A and an element B. Right, and those are going to map to other elements inside R, namely A plus B and A times B. Right, and so you're going to have some mapping occurring here. Okay. Oh, sorry about that. Let's get that on the screen there. Okay, so you've got this mapping, A and B, well, obviously mapped to other elements when it added together and when multiplied. Okay, and so if we have a mapping from R to S, right, that means B is going to map over to phi of B, and A is going to map over to phi of A. Okay, and then inside of S, naturally these elements are going to combine to give you phi of A plus phi of B and phi of A times phi of B. Right, and so I probably won't draw all of these, but you can imagine how these can combine, obviously, in the same way that we see on the R side of things. Now, these mappings, this is phi. This is the homomorphism phi. Okay, and so when I add two elements together in R, I get A plus B, and I better get the comparable element in S under phi. And that's all this condition here is concerned with, right? So when I combine A and B over here, I get A plus B. And when I map A over here, I get phi of A. When I map B over here, I get phi of B. And so when I add those together, I better get what A plus B maps to. And indeed, that's what happens, right? And then the same, obviously, is true of the multiplication. Okay, and so this is a nice schematic that represents the ring homomorphism concept. Okay, right, and it helps to underscore exactly why these are the conditions that need to hold in order for a mapping to be considered a homomorphism. Okay, all right. Let's see some examples of ring homomorphisms. Some of these are fairly easy, but let's just get them out there so we can have an idea in our head when someone says ring homomorphism. We can have some examples to pull from. So then first one we'll look at is for any integer n. For any integer n, the mapping k to k mod n is a ring homomorphism. Okay, and it's specifically a ring homomorphism from integers to the integers mod n. Okay, and we can show this by just considering phi of a plus b. So let a and b be any integers. Then phi of a plus b is going to be a plus b mod n. And we know that this is the same as a mod n plus b mod n, right? And so then, of course, that is just phi of a plus phi of b. Okay? So addition is preserved. And what about multiplication? Well, similarly, a times b mod n can be broken up into a mod n times b mod n. And that, of course, is just phi of a times phi of b, right? So this is a very simple, nice simple one to start with. Okay, and so that's the conditions that need to hold in order for a mapping from a ring to be a homomorphism. Okay, very good. Let's look at another example. Okay, another example, we'll take a look at, let's see. So let's so the mapping phi from the complex numbers to the complex numbers given by phi of a plus bi equals a minus bi. This is a ring isomorphism. Okay, so this is a ring isomorphism, and so we'll show how it preserves the operations, and I'll leave it to you to show that it's one-to-one and onto. And I think that's fairly easy to do. But let's see how it preserves operations. So we'll let A equal S plus Ti, and we'll let B equal M plus Ni. All right, so remember these are complex numbers. And so then let's consider the additive part first. So phi of A plus B. Right, so if A is S plus Ti and B is M plus Ni, we're going to substitute all that in. So this is phi of S plus Ti plus M plus Ni. Okay, and so we can combine inside the argument here. And we get, well, we would combine the real parts and then we combine the imaginary parts. So this is phi of S plus M plus t plus n I, right? And then when we evaluate, using phi, then this becomes a minus. So this is s plus m minus t plus n I. Okay, so that's what phi does. And so then let's rearrange this thing and see if we can recover phi of a plus phi of b. Okay, and so this is equal to, let's see, s minus ti plus m minus ni, and that's equal to, of course, this is phi of a, s plus ti becomes s minus ti under phi, right? And this is phi of b, because m plus ni becomes m minus ni. Okay, so we get back to what we need, right? So the operation is preserved under addition. And what about with multiplication? We'll do something similar, phi of ab. And so this one is going to require a little bit more work, but nothing we can't handle, right? So a is s plus ti, and b is m plus ni. Okay, and so let's go ahead and multiply this out. And we get sm plus sni plus tmi minus tn, right? So be careful, t times n times I squared would be minus tn, right? So just keep that in mind here. And then we can rearrange this, and we have phi of sm, put the real parts together, sm minus tn, and then plus sn plus tm I, right? So taking the imaginary parts and putting them together. And now let's evaluate with phi. And so this becomes sm minus tn minus, right? The sign flips, and you get sn plus tm I. Okay. And now we just need to do a little more rearranging, right? And so this is sm minus sni minus tmi minus tn. Okay, and now here's the little algebraic trick, sm minus sni minus tmi plus tn times I squared, right? So I, remember, is the square root of -1. If I square that, I just get a -1, and so that's what allows me to make that switch there. And then I can factor this. This factors out nicely, so I get factor an s out of the front, and I get s minus t I, and then I get m minus ni. Okay. And so yeah, just be careful when you go through that factor, make sure that that makes sense. But of course, this is just phi of s plus ti times phi of m plus ni, which is phi of a times phi of b, right? So there we go, we got that one. And again, the one-to-one and onto component can be shown. You can just spend your time on that one. That one's easy enough to show. Right, but that's a nice example. Okay, let's take another example. Let's try to get a little more out there. How about this one? Let's let R of x denote the ring of all polynomials with real coefficients. So this is the ring of all polynomials with real coefficients. Okay. Then, right, the mapping phi from R of x to the real numbers given by f of x, so some polynomial with real coefficients, maps to f evaluated at 1. This is a ring homomorphism. Okay, so this one is a little trickier to show. In concept, though, this is a nice example, right? I mean, basically what this is saying is that, hey, look, if I take all possible real value polynomials, this is a mapping from those polynomials to the real number line, right? Basically, it's simple mapping. All you do is evaluate the polynomial at 1, and in doing so, it maps to the real numbers. It's a homomorphism, right? So obviously, a lot of polynomials would map to any given real number, right? So it's not isomorphic, but it is a homomorphism, right? So kind of a clever example there. Okay. How about a little bit of a counter example? So let's think about the group of even integers. We know this is a group, and we typically would denote this as just 2z. So the group of even integers, 2z, is group isomorphic. It's group isomorphic to the integers, right, under addition. Right? So if you take any element, any even element, and you can map it, you can use this this fact, the group of even integers is group isomorphic to z, right? But is it ring isomorphic? Does the same principle hold for rings, right? No, it doesn't work for rings, right? But it is not ring isomorphic to z. Right, now what's missing here? Well, 2z doesn't have an identity element, and multiplicative identity. It doesn't have a unity, right? And so this one doesn't work out for that reason. Okay. And then here's a nice example also. Let's let R be a ring with the characteristic of R equal to 2. Okay, what do we mean by characteristic? Let's remember that. We talked about that a couple lectures back. So characteristic 2 implies that for all A in the ring, A plus A equals 0. Okay, remember that. So characteristic n just meant a plus a plus a dot 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 n times equals 0, right? Or another way to say it would be 2a equals 0 or na equals 0 if it's characteristic n. Okay, so if R is a ring with characteristic 2, then phi, a mapping from R to R, given by phi of A equals A squared, is a ring homomorphism. Now, why is that? Well, let's see here. Let's let A and B be two elements in our ring of characteristic 2. Then let's just check the conditions. So phi of AB we'll start with. This one is the more obvious side of the thing. So phi of AB, well, that's just AB squared, which is A squared, B squared, which is phi of A, phi of B. Nothing novel to report there. That one works. What about the addition side? A plus B. Well, that's A plus B squared, right? And when we square that out, we get A squared plus B squared plus 2AB. And because the ring has characteristic 2, this thing here is 0, right? 2 times A is 0, 2 times B is 0, because A and B are both in the ring. And so this is just A squared plus B squared, which is, of course, phi of A plus phi of B. Perfect, right? So that's why it works. That characteristic equal to 2 makes it work. makes the addition property work. Okay, excellent. All right, so there's a bunch of examples, and there's, countless examples. Which is just a couple of that I identified. Let's take a look next at the obligatory properties theorem. All right, so we have to go through this. We won't prove any of these. Many of these proofs go back to group homomorphisms and can be easily extended to involve the ring as well. Right, but I will write it out, and we'll talk briefly about some of these properties. So let's let theta be a ring homomorphism. From a ring R to a ring S. Okay, and let's let A be a subring of R. Okay, so we've got a subring on the R side of things, and let's let B be a subring of S, but not merely a subring, but an ideal of S. Okay, so on the one hand, we've got A as a subring of R, and on the other side, we've got B as a subring ideal subring of S. Okay, then, all right, so let's list some of these bad boys out here. So the first property is for any R and R, any element in the ring R, and any positive integer, okay, for any element in the ring and any positive integer, we have phi of n times R equals n times phi of R. Okay, so that's something that we had back with groups as well. And also phi of R to the nth power is equal to phi of R all raised to the nth power. And so again, something we had with group homomorphisms, a property that holds also for rings. Second, so remember A is a subring of R, and so phi of A is the set of all elements from A mapped under phi. This is going to be a subring of S. So we saw this also with group homomorphisms, right? If I start with a subgroup and I map the subgroup, then I get a subgroup on the other side of the mapping as well, right? So subgroups map to subgroups, and here we see subrings map to subrings. Nicely, probably anticipated, but only because we've seen these things before. Okay, and so all we've done is add some complexity in the case of an additional operation. The third property says if A is an ideal, right? So it's A is a subring, but if it's an ideal subring, and phi is onto S, okay, then phi of A is an ideal also. All right, so if I've got an ideal subring, then when I map the ideal subring, I get an ideal subring on the other side of the mapping. That's only in the case where phi is onto, right? And I think if you try to prove this, you will see exactly why that is the case. Right? That is definitely necessary. All right, very good. Number 4, phi inverse of B. All right, so remember B is a ideal subring of S, and so phi inverse of B, what is this? This is going to be all of the R in R, all the elements of the ring R, such that phi of R is in B. Obviously, that's one way to write it. So if I start with an ideal on the one side, on the image side of the mapping, then the inverse mapping of that ideal is an ideal on the domain side. Okay. All right, so kind of the same idea as the previous one, except kind of in reverse. Right, in reverse. All right, and also the condition is lightened slightly. It doesn't require that phi be onto in this case. If you start with an ideal in the image, then it will map to an ideal in the domain side. Okay, very good. If R is commutative, then phi of R is commutative. Right, and we saw something similar for group homomorphisms. I mean, this just, again, this really is just taking literally the idea that that R and S are really the same group. They're just wearing different clothes, basically. Okay, so if one side is commutative, then the other side must be commutative as well. All right, and if R has a unity 1, right, so it's got a unity, and S is not equal to merely 0, and phi is onto S, then phi of 1 is the unity of S. Okay, so that one's a little bit hairier, right? So if R has a unity, right? So if it's a ring with unity, and if S is not just the trivial ring of just the 0, and if phi is onto S, then whatever the unity is in R, i.e. phi of 1, i.e. 1, then the mapping of 1 is also going to be the unity on the S side. Okay, so this one is, there's a couple of conditions here that you have to be like weary of. Like, you might be inclined to say, yes, of course, whatever unity is in R, phi of that is the unity of S, but it does require some additional conditions, right? Remember that a ring doesn't necessarily have a unity, right? So that's the main thing to keep in mind when you try to prove this one. Okay, and so that's why the need for some of these other conditions. All right, 7. Phi is an isomorphism. Right, so we're talking phi is automatically a homomorphism by assumption, but it's also an isomorphism if and only if phi is onto, right, and the kernel of phi, let's remember what that is. The kernel is going to be all of the elements in the ring R such that they map to 0. Right, so phi is an isomorphism if and only if phi is onto and the kernel is equal to just 0. Okay, so this is, I mean, we know an isomorphism is 1-to-1 and onto, and so here we straight up say that phi needs to be onto, but then this kernel having just a single element in it, that's a way of kind of saying 1-to-1 without saying it. Not exactly, but sort of. It's a way of getting around that. And then the last property that we'll mention here is this one. It says that if phi is an isomorphism, from R onto S, right? If phi is an isomorphism from R onto S, then it's an isomorphism, it's 1-to-1 and onto. That means we can reverse the mapping. Then phi inverse is an isomorphism the other direction. From S onto R. Exactly like we saw with groups. Okay. All right, and so these are the 8 big properties we want to call out, and I think the main, we're not going to prove these. I think the main purpose in calling them out, obviously they're important to know, but is just to see how, really ring homomorphisms are a natural extension of group homomorphisms. You just add that additional operation in there, but the whole concept is very, very similar, right? Almost identical. All right, and then in a similar vein to what we just did with the properties, we've got a handful of theorems that are going to be very, very parallel to theorems we saw with group homomorphisms, but we're going to walk through them anyways. Okay, and so the first one says that let's let phi be a homomorphism. Let phi be a homomorphism from a ring R to a ring S. Okay. Then the kernel of phi the kernel of phi is an ideal of R. Okay. When we were talking about groups, what we would have said instead is that the kernel of phi, a group homomorphism, is a normal subgroup of R. And that's what we would have said previously in the case of groups. But here we replace the normal subgroup concept with the ideal concept. Okay. All right. Very good. And the next theorem, again, similar to the ones we've been talking about. Let's let phi be a ring homomorphism. Let phi be a ring homomorphism from a ring R to a ring S. Then the mapping of R mod kernel phi to phi of R given by R plus whatever the kernel of phi is maps to phi of R. This is an isomorphism. Okay. So in symbols, what the notation we might be more comfortable with is R mod kernel of phi is isomorphic to phi of R, right? So if phi is a ring homomorphism from R to S, then the mapping that takes an element from R minus the kernel of phi to phi of R, given by R plus curve phi to phi of R, this turns out to be an isomorphism. Okay, and we'll use this theorem in the coming section. This is what's referred to as the first isomorphism theorem for rings. Right? So this is the first isomorphism theorem for rings. It's sometimes called the fundamental theorem of rings. Okay. All right, and then one more, again, that matches or aligns well with group homomorphism theorem that we saw. Every ideal of a ring R is the kernel of a ring homomorphism of R. Okay, is a kernel of a ring homomorphism of R. Okay, so a way to kind of say this like more in particular, in particular, right, the mapping, well, so in particular, an ideal A is the kernel of the mapping that takes an element R from the ring and maps it to R plus A, right, where A is an ideal, right? And of course this is a mapping from R to R mod A. Okay, so this is let's see an example of these. So these three theorems kind of in action here. Okay, so let's see an example. So the mapping from Zx, right? And so what is this? This is the set of all polynomials with integer coefficients. The mapping from Zx onto Z that's given by, right, and so here's the phi of whatever f of x happens to be. F of x is in Zx, of course, integer polynomial. So when we map f of x under phi, we basically evaluate it at 0. Okay, so the mapping from the ring of integer polynomials onto the integers given by this mapping here is a ring homomorphism. And it's a ring homomorphism. Now what's the kernel? Right, what is the kernel? Well, the kernel is basically kernel of phi is equal to basically this, right? It's just going to be x and the set generated by this element. And what is that set? Well, that's just x, x squared, x cubed, and so on. All of these are obviously going to map to 0, right? Because anything else won't map to 0. It'll have some additional coefficient, right? And so this is the kernel of phi. Okay, and then so by the theorem we just discussed, so by the previous theorem, what we would say is that the ring of integer polynomials mod the kernel here is got to be isomorphic to the integers. Okay. All right. Now we actually know, right, that Z is, not merely a ring, but it's actually an integral domain. But notice it's not a field, right? It does not have multiplicative inverses, right? So what we actually know instead is that the ideal X, right, the ideal, this set here, this set is actually prime. It's a prime ideal. In Zx. And so you have to go back and take a second and think that through, make sure that makes sense. Go and remind yourself of what a prime ideal is and confirm that this guy here is actually a prime ideal. It has to do with the fact that the integers are an integral domain, but not a field. All right, very good. Okay, now we're going to have we have a string of theorems that we need to look at here that are just some nice, that connect the idea of a ring homomorphism to some of the other things that we've seen in rings so far. But ahead of that, we do have this kind of utility theorem that we need to get out of the way. So this theorem will be used in a couple of coming proofs. right? It's just easier just to prove the thing by itself. Right? It's kind of a straightforward thing, but let's let R be a ring with unity 1. Okay. The mapping phi from the integers to R given by n maps to n times 1 is a ring homomorphism. Right, and so again, this is a what I would call a utility theorem. It's very useful in some of the proofs that are coming up. Okay, so we're basically just saying, look, I've got a ring with unity 1. There's this mapping from the integers into this ring that is given here, and indeed this mapping is a ring homomorphism. Okay, let's prove this quick. So what do we got to prove? Well, we got to prove that it preserves operations, right? And so we'll start with the addition operation. And there's going to be 3 cases. So we'll start with addition, and there's 3 cases. Right, so the case 1 would be where the 2 elements are both positive integers. Case 2 is where they're both negative integers, and case 3 is where one's positive, one's negative. And you got to kind of take them separately because just the arithmetic looks different. So case 1, m and n are both greater than or equal to 0. So phi of m plus n equals, well, it's just m plus n times unity. And so that's just equal to 1 plus 1 plus dot 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 plus 1. How many of them? M plus n. And we can break that up into 1 plus 1 plus dot 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 plus 1 plus 1 plus 1 plus dot 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 plus 1, where you've got m of them over here, and you've got n of them over there. And of course, this is m times 1 plus n times 1, which is phi of m plus phi of n. Okay, so in the case of both positive or 0, anyways, it's straightforward. Okay, so then case 2, we'll let them both be negative. And so we just have to be a little careful with the arithmetic here. Case 2, m and n are both less than 0. All right, and so phi of m plus n is equal to m plus n times 1. And that's equal to negative m minus n times negative 1. All right, so you can see why that would work. All those negatives would cancel out and be the same thing. Right? And so this is equal to negative m times negative 1 plus negative n times negative 1. And that's equal to m times 1. Hold on. Equal to m times 1 plus n times 1, which is phi of m plus phi of n. Okay. All right. Okay, and then so then case 3, we'll say m is greater than or equal to 0, and n is less than 0. Right? It doesn't matter which direction you go with that. Okay, but in this case, you kind of do the same thing as above, but you just sort of do each of them, treat each of them slightly differently. Okay, and so phi of m plus n is just m plus n times 1, which is equal to 1 plus 1 plus dot 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 plus 1, m of those, plus 1 plus 1 plus dot 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 plus 1, n of those. Actually, this is a minus. Let's make that subtracting, right? So we got to pull the negative out. Okay, and how many of these? Well, there's absolute value of n, right? There's not negative. N is a negative number, remember, so I have to say absolute value of n. All right. And then the m times 1 here, And then over here you've got negative n times negative 1. Right? And so this is just m times 1 plus n times 1, which is phi of m plus phi of n. Okay, and so all three cases work. The addition is preserved for all three cases in this case of a general homomorphism. Now for multiplication, that can all be done in a single case. So for multiplication, we'd say that phi of mn equals m times n times 1, right? And this is just m times n times 1 times 1. And so we know that this is m times 1 times n times 1, which is just phi of m times phi of n. All right. Okay, so there's that, right? So we've got a homomorphism here, right? And again, we're going to need this for a coming proof. Okay, so we're going to need this for the next two theorems, actually, right? And that'll be kind of what we wrap up ring homomorphisms with, these last two proofs. Okay, and so the first of the two is this guy. The first of the two says that if R is a ring with unity, and the characteristic of R is equal to n, which is greater than 0. So this is does not have characteristic 0. Then R contains a subring isomorphic to Zn. Okay. Right, so let's pause. There's a second part to this, but let's just think about this for a second. So R is a ring with unity, right? So it's a ring that has a multiplicative identity, and it's got characteristic n. Then automatically this ring is going to contain a subring that's isomorphic to Zn, to the integers mod n. Okay. So R is automatically going to contain a subring isomorphic to Zn. Now what happens if instead of the characteristic being n being greater than 0, what if the characteristic is 0? So if the characteristic of R equals 0, then R contains a subring isomorphic to Z, to the integers themselves. Oh, okay. So that's kind of a big theorem. Every ring with unity automatically is either isomorphic to the integers or is isomorphic to the integers mod n. Okay, this shows like kind of a deep connection between rings in general and the characteristic of the ring that you're dealing with and these integers. Okay, so let's prove this one. Let's prove this. Again, this is going to draw heavily on the proof we just worked out, which was that utility theorem. So let's let 1 be the unity of R. Okay. So 1 is going to be the unity of R. And let S equal the set of k times 1 such that k is an integer. Okay, our previous theorem, the one we just got done with, told us basically that, hey, there's a mapping from integers to S. Our previous theorem showed that there is a mapping from the integers Z to S given by phi of k equals k times 1. And also that phi is a homomorphism. Okay. And that phi is a homomorphism. All right. So then, by the first isomorphism theorem, what was the first isomorphism theorem? All right, the first isomorphism theorem said that if phi is a ring homomorphism from R to S, then the mapping R mod cur phi to phi of R given by R plus cur phi. So basically it said that R mod cur phi is isomorphic to phi of R, right? And so by the first isomorphism theorem, in this case, by the first isomorphism theorem for rings, we know that the integers mod cur phi is isomorphic to S. Okay. All right. but the kernel of phi, what is the kernel of phi? Kernel of phi is just this. Right? It's this guy here. And what is n? N is the additive order of the multiplicative identity. Okay. So kernel of phi is just this set generated by n, where n is the additive order of the multiplicative identity. And by the theorem, the characteristic of R then is equal to n, right? Because this is n is the additive order of the multiplicative identity 1. And by theorem, we saw previously that, if you know the multiplicative if you know the additive order of the multiplicative identity, that automatically is equal to the characteristic. And so here we know that the characteristic R is equal to n. So when R has characteristic n, then what do we have? Well, we have that S is isomorphic to Z mod n, which is isomorphic to the integers mod n. And of course, when the characteristic is 0, this same thing is true, but you just replace everything, right? And so instead you have S is isomorphic to Z mod 0, which is isomorphic to not Z mod n, but the integers themselves. Okay, so that's the idea. All right, so kind of a complicated weaving here, but obviously relies a lot on this other theorem that we just talked through, this utility theorem. But once you have that, it really is just a piecing together of the conditions of previous theorems that we've looked at and just evaluating what they all kind of lead to. There's nothing in particularly clever here happening, right? This is all just the previous theorems being plugged into one another. All right. And so one last thing here on this, one last theorem. And this one is not as difficult, but what this one says is that for any positive integer m, the mapping of phi from the integers to the integers mod m given by x goes to x mod m is a ring homomorphism. All right, so this is just a very easy mapping that we can always use whenever we want to generate a homomorphism from the integers to integers mod m, right? And it turns out that this is always a homomorphism. This follows directly from our previous theorem, right? So we're not going to write the proof, but you can think of it like this. In the ring Zm, the integer, you can think of it like this, the integer x mod m is just x times 1, right? That's all it is. It's the same idea as what we had in that utility theorem, right? So for example, in Z3, if x equals 5, we have 5 times 1 is equal to 1 plus 1 plus 1 plus 1 plus 1, which is 5, which is equal to 2 mod 3, sorry. Right, and so you get the same, that's where that comes from, right? And so you can use that previous theorem to show this. And you could spend a little more time fleshing this out a little bit further if you want. But all right, so that's where we'll leave off here. And when we pick up next time, we've got, I think, 2 more lectures that we'll do. We'll talk next time about polynomial rings, and then we'll end with, we'll end with polynomial rings, really. We're going to talk about polynomial rings themselves, and then talk about factorization of polynomials. Right, so I think these topics will, sometimes these homomorphism lectures can be a little hairy. They just, they're a little far afield, from the way we normally think about algebra. Normally think about algebra, not necessarily abstract algebra. But I think in the next lecture, we'll talk more about polynomials, and that's a ring and a ring structure. It's very important and very compelling. But it's also just a little more like down to earth. We're more used to thinking about those types of structures. So that's what we'll do next time, and then we'll just dig in a little bit deeper in the final lecture and discuss factorization of polynomials. All right. Till then, take care. See you all later.